your trademark. But the reason is I wasn't actually sure how to give a talk or not, and I think on the web page it wasn't obvious how to say maybe. So I said yes with an if or yes with a but. I'm not sure which one it was. So I said yes, but decided to say, well, maybe I'll give a title, maybe not. And organizers were kind enough to, I think, realize that I may not be speaking at all, so I put my talk at the end of the day. So if I somehow cancel, it will still be on time. But of course, these things have a life of their own. Once your name is in the program and then there is even some TBA, you feel obligated to say some things. But I wasn't sure what to even talk about. I have some talk prepared, but I decided to say something else at the beginning, even if I don't come to the original talk, it's fine. It's no big deal. Because Warren this morning, he explained polar codes with, I think, 2 equations or 1 equation and 1 inequality. But I think that's not quite enough to explain polar codes. I think part of the audience may not know this, and part of the audience may know this, but they may want to teach in their class or something. And I think I have a reasonably clean way to explain these things, perhaps to be teachable in, say, undergraduate class or something like this. If you want to do this one, it might perhaps be a useful exercise to go through. That should be hopefully short, if I don't talk myself out of time by going blah, blah, blah like this. Okay. So so now the whole structure of polar codes is depending on a very simple transformation. You start with 2 copies of a communication channel, which I'll call to be W. This channel is going to be binary input. So the channel input is something from the binary field comes in, but the output can be whatever you want to be. The output of a bit is not particularly not even discrete even. And to this one you apply a very simple transformation. This one. So these are also binary field objects, U1 and U2. You take their modulo 2 sum, you send them over the first channel, and you take a second one of these U's, the U2, you send over the second copy of your channel, you say this. Now this looks like you haven't done anything at all, right? So first of all, the things that you notice is that the U1, U2 is in really one-to-one correspondence with the child inputs x1, x2. One determines the other, so this transformation is not really doing anything useful, okay, it seems. Okay. However, by doing this and by imposing a decoding order, you say, I'm going to look at the output of this channel y1, y2, and I'm going to first decode u1. After I've done this, I'm going to decode u2. If you put this constraint, what you have now done is to synthesize 2 synthetic channels. One is the channel which is sitting between u1 to y1, y2, from which you're going to decode the u1. Let me call this channel w minus. The reason for the minus sign to become obvious shortly. And then, of course, once you have decoded the u1, hopefully correctly.
U2 here. U2 here, right?
No, u1. Okay, so trust me. I've done this more than once. Then again, don't actually. I apologize. Don't trust me. Actually, this is because the.
It's easy to decode U2 because you have it.
This is W plus, right?
Yes.
Is this W plus?
No, this is W minus. Trust me also. You trust me too. All right. So now, once you have decoded the U1, hopefully correctly, you're going to decode the U2 from the output of the channel, which is, since you have already coded U1, you have access at the output to the value of U1. Even if it is wrong, I'm going to count your error anyway already. So that you have already made an error, so that doesn't going to hurt me because the error is a block error I'm going to worry about. The block error already happened. So the error event that the estimates are incorrect is already counted in these, and the first one counts the U1, and then no need to consider the possible error in the first thing. This one I'm going to call to be W plus. Okay. All right. Now, perhaps I should do a simple example in here. Suppose that your channel was the binary erasure channel. Okay? So this y1, y2s are either equal to the corresponding x's or they're erasures. Okay? All right. Let's take a look at the channel W minus. Okay? So now, if you get both symbols correctly, you get x1 and x2, from which, of course, you can figure out what is the value of u1 is. So if there are no erasures, you get your u1 correctly back. Okay? Suppose though the first one is erased, okay? So this y1, which is the x1 is erased, okay? And you obtain the x2. Well, x2 is u2. Oh, very nice, but this is completely useless from the point of view of the u1. So the erasure in the first symbol is an erasure channel already. On the other hand, if the second one is erased, okay, then you want to figure out u1, but you obtain x1. x1 is u1 XORed with a binary coin flip. It is equally useless. Okay? So either erasure is a disaster for you. The only good thing is that if both channels don't erase. So this W minus, so if W was a BEC of, let's say, erasure probability P, then W minus is a BEC with a unerasure probability of 1 minus P squared. So the erasure probability is 2P minus P squared. Okay? So we have this. At the same time, if you now take a look at what is W plus, you will figure out from the same argument that unless you have both erasures, you're okay. The only disaster is both the channels have to erase because you have the value u1 for free and so on. This helps you a lot. W plus becomes BEC of P squared. Okay? All right. So what you see is the following. You start with 2 copies of an identical channel with erasure probability P. But what you have created at the output is disparity. You have created an equality among the channels, even though on the average they're the same. So these 2 channels on the average are as good as the original channels there, okay? Because the sum of these 2 numbers divided by 2 is the same as P. Okay?
So, but in the second channel, you allow me to see u1 in the clear.
Yes, because I ask you to.
Why is that fair?
Because I insist that you decode the W minus channel first. Okay? So whatever you do, you decode W minus first, and then you have the U1 in your hands. Okay? Okay. Good. So now we have this. Now, a few properties of this is the following. So first of all, if you compute the mutual information developed across W, and the mutual information developed across W minus and W plus, what you see is you have some sort of a conservation property, which is this one. This is coming from simply the fact that you have this one there. Okay? That's you haven't done anything. These 2 channels together are the same as the 2 copies of your W. So twice the capacity of W is the same as the sum of the capacity of W minus W plus. So you have conservation of mutual information. And then secondly, as we saw here, the plus channel is better than the usual, the standard original channel, which is in turn better than the W minus channel. And to see this one is extremely easy because of the following. Take a look at the channel between the W plus. We have U2 here, Y1, Y2, U1 there. The channel that's sitting between U2 and Y2 is already W. Okay? So anything else that you have is extra stuff. So clearly this inequality then must be true. Okay? In light of this, then this must also be true, right? Otherwise you would violate the conservation. So we have that. Okay? Now, second thing, well, I'm not sure second. I cannot count. Okay, so I can compute averages, but I cannot count. Now, if you took a look at so this was the average. Okay, I can also take a look at the thing with the minus sign. I can plot here W plus minus W minus divided by 2. I give you so this one we know. If I put a plus sign here, you get IW itself, and you put here the IW like that. Okay. So now, if you take a look at the erasure case, okay, the difference divided by 2 is simply P times 1 minus P. Okay, this is okay. So this will be the plot. So the IW is 1 minus P. You're plotting 1 minus P versus P times 1 minus P. You'll get this kind of a curve. Okay, so 0 to 1. This moment 1/2. Okay, so far. This is for the erasure channel case. In fact, this kind of plot is true for any channel that you want to. So no matter what W that you started from, okay, what you're going to have is the following. In fact, the erasure is the most disparizing, okay, if you wish. Okay. Every channel here is lying somewhere in between. No matter what W that you start with, if you plotted the IW on the capacity of the channel W on the x-axis, and the difference of the capacity of the good and the bad channels on the y-axis divided by 2, you'll get a plot like this one. Everything is inside here. The proof of this is a simple consequence of what the information theorists call the Mrs. Gerber's lemma. it's a simple thing to prove, okay? And the name is Mrs. Gerber. Well, in a longer talk, I'll give you a story, but okay, fair enough.
Mrs. Bergerstein.
Mrs. Bergerstein, yes, that's a different burger. That's a cyclic shift. All right, so let me call this lower line, let me give it a name. Let me call this thing, since it's lower lambda, okay? So let me call this thing to be so we have this lower bound lambda, okay? Let me call this lambda of epsilon. I don't know why I'm calling this thing to be epsilon. Let me also define a quantity which is running out of space. But can you see this from the back? Maybe not. Yes? No? Not from the camera, that's for sure. Okay. All right, so I'll do it here. And this, let me call kappa of epsilon to be the minimum of lambda epsilon and lambda of 1 minus epsilon. Okay? This is saying that, so first of all, if you put here epsilon and 1 minus epsilon there, okay? So if you take channels which are moderate, they're neither very bad in terms of capacity, nor very good in terms of capacity. If your channel lives somewhere in here, if your original mutual information is somewhere in there, okay, then this is saying that you'll create disparity at least by this amount kappa. Okay, this is the that's saying that you'll be creating disparity at least by that much. Okay, all right, fair enough. So now that we know all these properties of the single polarization step, let's see what I can. I'll go now repeat this process repeatedly. I guess is a repetition. How repeat this process multiple times. So you start from channel W. Okay, you can now create this. You created these two channels. Nothing prevents me from applying the same transformation to these things. So what we're going to create is that the plus of the W plus and minus of the W plus, plus of the W minus, and then so on and so forth. Okay, all right. So now we have this going off diagram like this. Now I can compute on this in this object a few statistics. Okay, so here's what I will compute. Here I'm going to take the following thing. I'm going to take a look at a particular column. Okay, there are these 4 channels here. For each of these channels, I'm going to take a look at their mutual informations, this I of these channels, okay, and compute their numerical average, arithmetic average of these 4 numbers there. Let me call these numbers to be mu. Okay, I start with mu0, which is equal to the I of the original channel W. Okay, I have mu1, which is the average of the mutual informations of this. Of course, because of this statement here, mu1 is nothing but mu0. For the same reason, mu2 is nothing but mu1. So this is a constant line. This is a very uninteresting computation. So I only obtain a sequence of constants. Okay, fine. Okay, all right. The second thing I will do is to do the following thing. This is the first moment, if you wish, of these columns. I'm going to compute their second moments. Why not? Okay. Now, let me call it to be news. Okay, so this starts with I of W squared. Okay, and then on this column I have mu1, mu2, mu3, etc. Okay, all right. So now, what can we say about these news? This is actually a question. All right. So now let's take a look at this thing once more. I'm panicking about what to erase. I guess I can erase this one. This is fairly safe at this moment. So the following fact is obvious. If I take the average of squares is bigger than the square of the average. Right. In fact, it is bigger exactly by the amount which is the this half difference squared. This is equality, right? So it is bigger than this by exactly this particular thing there. So now, if you take a look at the IW plus and IW minus, their average is IW. Consequently, the average of their square is bigger than this one. So you have this for free, this, like that. Okay, so for the same reason, this thing propagates. So every step creates a second moment. And of course, these numbers, by the way, they're upper bounded by 1. Because all these mutual informations that I'm computing are upper by 1 bit. So I'm taking averages of numbers between 0 and 1. So these i's, these news are increasing sequence upper bounded by 1. Okay. At the same time, let me also compute a third statistics. Let me call it the something else. Any suggestions for this? Mrs. Robinson's lemma. I see. They're going to sigma. Okay. So these are going to be the following. So this sigma is going to be the following. So sigma I, or sigma n, if you wish, is the fraction of moderate channels. The fraction of these channels that are in this column, okay, which happen to have mutual information between epsilon and 1 minus epsilon. These haven't become neither good nor bad. Fraction of, let's say, epsilon moderate channels. So I count how many channels in this particular column have mutual information still in this interval. Okay, and I divide by total number of channels that you have in this column. I call these to be these sigmas. Okay? So what you see is the following. So the first thing that you observe is that this, if you take a look at how much does this nu n increase, I just put down this inequality signs to these news. You'll see the following thing. This nu n plus 1 is bigger than nu n, okay, by at least this kappa epsilon times sigma n, because each of these immoderate channels, so each of these moderate channels, okay, is going to contribute at least this kappa epsilon amount of disparity. This is okay, disparity to the variance. Okay, so we have this inequality there. All right, very good. So now essentially we're done. Now to see the following, these news are an increasing sequence which is bounded. Consequently, they converge. They have a limit. Okay. In particular, difference between nu n plus 1 and nu n, this thing goes to 0. Okay. But this guy is an upper bound to the fraction of moderate channels. Okay. If I divide this thing by kappa epsilon squared, okay, this is just a constant, depends only on epsilon, not on n. Okay. This top guy is going to 0 as n goes to infinity. Consequently, sigma n converges to 0. So this process of doing this operation, you'll end up with no moderate channels will survive this process. At the large column, you're only going to find channels which are either mutual information very close to 1 or mutual information very close to 0. Okay? And the first one here, saying that you actually preserve mutual information at each column, means that the fraction of these good channels, the ones which have mutual information close to 1, must be in fact exactly equal to IW, because the other ones are all 0. Okay? So this one says, yes, polarization happens, okay? And the polarization creates the correct number of good and bad channels. The number of good channels that you get is exactly the capacitor original channel that you started from. And if you wish to build a communication system, a code out of this, you will simply put information through the good channels that you created, and you will send no data over the bad channels. Okay, all right. So that's perhaps for the information theorists, coding theorists among you. This might be something that you can actually teach in a class within whatever allotted time for something, without going into martingales, blah blah, so on. Okay, you only have to pull out the Mrs. Gerber's lemma out of your hat. But that's something that people have to prove anyway at some moment in these courses. So it is not a. Okay. So now I think I'm okay with what I wanted to sort of say for this particular thing.
How did we avoid? So this is a foolproof, right?
It's a foolproof, yes.
So where was the technology of the martingale crucial, and how did we dodge it here?
The martingale proof was necessary in the following way. The martingale proof would have said, okay, let me now make a random walk in this tree. I just go up or down and so on and so forth, like this one. This is a bounded martingale, must converge. Okay, since it converges, you must have the subsequent two things to be the same. But because of this, they cannot be the same unless you're converging to here or here. Okay? So I'm essentially, but you require this martingale in a very naive way, okay? Because the martingale proof says that you have a convergent sequence, okay? this is only saying I'm using a sequence which is simply successive things which go to 0, which is much weaker than a convergence statement, right? So even the original martingale proof, the martingale-ness was used in a very weak way. So essentially, hence I can discard the martingale business and use something which is much weaker.
So yes, doesn't that the proof doesn't imply also that it converges as a as a random variables, because the new n goes to 0, then that gives that along each edge the difference must go to 0?
Well, to prove a sequence is converging is not sufficient to prove a successive thing terms come close to each other, right? That does not mean convergence.
Yeah, but you can take any new n and new n pi.
Okay.
Is there like a less strong result than do? That would be if you have a process with orthonormal increments?
That's absolutely. This is exactly this. Okay. Okay. So if you wanted to state in this term, this is exactly the orthogonal increments process has to have blah blah. Okay. So now, now that I've sort of done justice to this polar stuff, should I talk about something else? How much time do I have?
So you started 5 minutes late. So technically, you have 7 or 8 minutes. I think.
Well, let me at least state something so that I'll say something new.
Can we 8 is
Yeah, it should be fine. Okay, I'll skip a million slides. Okay, that's fine. Okay. No, we're not negotiating. This is I don't need to actually talk at all, honestly. But okay. Now.
Winning strategy.
Yeah.
There's also something which I should not even be talking perhaps myself. Note the parentheses here. Maybe I should actually highlight them. Okay. Yes, it's very important, these parentheses. When I first read financial reports in American newspapers, I was completely confused by these parentheses. They apparently mean negative numbers. So I'm a negative author here. Okay. Perhaps not completely negative, because there were some certain other topics in which I was indeed negative author. So saying, okay, no, this is wrong, and so on and so forth. But in this case, maybe I'm simply a sort of neutral person. So I just put brackets. The work is actually mostly of Rajai, who's a PhD student of mine, sort of midway in his stuff, and he got interested by himself on a whole bunch of problems that I barely understand myself. But let me skip all this business for the polar codes. But just to say that I want to replace this plus sign, which we used heavily, in 2 places. One of them was to show that this transformation u1, u2 to x1, x2 was 1-to-1. That required this modulo 2 operation to have certain properties. And second was Mrs. Gerber's lemma, which also heavily relied on the fact that there was a plus in between. We had to talk about this plus business here. So I would replace this plus with a star. For the binary case, you can't do anything, because it's modulo complementations of stuff. You cannot do anything. But for larger alphabets, you can think of which operations that we can do. Eren had worked on these things for a while. First of all, if the input alphabet is a prime cardinality, then you can turn it into a simple abelian group by modulo addition like this. That would work. That will polarize. Other stuff in general abelian groups, you get something called multi-level polarization, namely polarization not to extremal channels, perfectly good or perfectly bad, but also things which are halfway in between, but still easy. Okay. All right. So now, the things also work if you have not just group structures, but quasi-group structures, meaning that you have both left and right invertibility, but no neutral element, anything of this type. Okay. So here's an example. Okay, you have the star operation, x1 times x2 gives you this table. It is not a group, but it's a quasi-group. This thing polarizes. Okay, all right. Eren had this very nice example in his thesis. One certain very simple quasi-group operation which polarizes every channel. He proved that one. Okay. Another thing is, so quasi-groups in general they always polarize. We know that too. Okay. So now, what you end up having to do to generate all this stuff is to look at partitions. Okay, so you take a partition of the input alphabet, okay, and then you define some strange operation saying that I take a look at the element-wise operations within the partition classes. Okay, and then you define this multiply doing this star operation onto partition elements. Okay? And then we define something called a stable partition if things begin to repeat. Okay. So here are some examples of stable partitionings. Okay. If you do 0, 1 and the 0, 1, okay, then the star operation gives you 0 and 3 because 0, 1 and 0, 1 gives you this. If you do 0, 1 cross 2, 3, you get things that are here, so 1, 2, okay, and then you see that the other one's also still the same. So this is and the next step is going to give you back, so this H is a stable partition because, like this. I'll skip all this polarization stuff, okay. Okay, I'll skip easy channels, okay. So now, you need uniformity preserving, this invertibility of U1, U2 to X1, X2. This is sort of obvious. You clearly need this, otherwise nothing will happen. Okay. And now you need some notion of ergodicity type notions to make sure that the polarization does happen. You sufficiently mix things together, otherwise things don't work well. Okay. So you say that you can connect an element of X with the operation star to some other element of X. Okay. If you can find some multiplication on the right, which will take the X, you multiply, you end up with you end up getting to the Y. Okay. All right. So for example, here there's a small diagram as to who can you reach from whom. Okay. This is 0, 1, 2, 3. All these diagrams, it's a cyclic order starting from 0, 1, 2, and 3. Okay. Now, irreducibility, for example, this one is irreducible because you go back and forth. Okay, you cannot reach everywhere. Okay. Irreducible means that you can reach everything from everything. So you can start with whatever 0, and then you can buy sufficiently nice things. You can reach all these other things. Okay. But this one, for example, irreducible but periodic. From 0 in even steps, you can only go to 1 and 3. Only in odd steps, you can come back to 0 and 2, and vice versa. Okay. Now, ergodicity means that you know periodicity, namely some L, it'll connect in L steps everything to everything in exactly L steps. Okay, that's ergodicity. And now, this is necessary. Ergodicity, if you don't have ergodicity, you won't have polarization. Okay? We first thought this might be sufficient. Okay, this should be in fact a sufficient condition too. Okay, but turns out no, because you see ergodicity is hiding too much of the actual structure of the group. Because this diagram here, you can decide ergodicity just by looking at this thing here. Okay? But this diagram hides by what multiplication did you go from A to B. Okay? This you don't know. You just simply went, but you don't know by which element. Okay? That's important. Okay? So this is not sufficient. You need something called strong ergodicity, which I'll skip all the details of. Okay? That is to say that this strong ergodicity is in fact necessary sufficient condition for the operation of polarizing. In fact, it's not the operation itself, but the left inverse of this operation should be strongly ergodic, which is checkable easily. Then, if and only if the operation star is polarizing. Okay. So with this, I think I will stop. I apologize for giving. One should only have one topic in a talk. That's semi-cardinal principle. I seem to have violated this one, but I hope that at least one. I think the first part probably went through. The second part might be a slight disaster, but so I'll stop anyway. Thanks. Thank you.
Questions for Emre? Okay, so
End of the day, so.
So if you
sorry,
applied this to, say, Z4,
Yes.
what would you find?
So the Z4, I apologize, I skipped a whole bunch of details which was actually important. Of course on Z4 you can come up with, for any alphabet you can find a quasi-group. So it's not a problem of given a alphabet X, can you find an operation polarizes? The answer is yes. Okay. So for any alphabet you can come with a quasi-group, for example, which will polarize. Okay. But you can check if any particular operation will polarize or not. Okay. On the Z4, we'll think of addition modulo 4. Okay. That will polarize, okay, but not to the usual Arkan polarization as to 0 or to 2 bits. There will also be channels which are 1-bit capacity, but also very easy channels. Okay. Those channels are also easy to decode. So this polarization is a slightly more general phenomenon I'm talking about, namely polarization not to purely extremal channels, but also to easy channels from which the output is easily decodable, essentially Block length 1 codes are good enough channels.
That was actually my question.
Right,
Your
okay.
polarization is slightly different. Than
Yes, the notion of polarization is slightly different. Well, it's the same for the binary case, so it's not clear if it's different or not. Okay. Yes, ma'am.
So the group is just important because you want closeness, you don't want to change the alphabet. So is this chain that you had there, that does it polarize because it enabled some kind of mixing?
Yes. Yes, that's exactly it, yes. If you don't have sufficient mixing among these different symbols, then you can, essentially to each of these necessary conditions, they're necessary because they're counterexamples. You can come up with a polar operation which is not ergodic, and then you can come with a channel. This channel will not be polarized under. You give me an operator not ergodic, I can come with a channel for which when you do this operation on it, the W minus W plus are in fact exactly the same as W itself. Okay, so it's essentially your process gets stuck. Okay, this W, it's not just that the mutual information does not move, the channel does not move. Okay, you end up with two channels which are completely equal to the channel that you started from, so no hope of ever producing anything.
Okay, let's thank Emre and all the speakers.